All right, so let's continue our discussion of oxygen nucleophiles. In the last video, we considered hydrates, where essentially we were adding water. In this video, we're going to consider the formation of acetals and hemiacetals, where alcohols is going to serve as the nucleophiles. So as I just mentioned, alcohols can serve as nucleophiles in these nucleophilic addition reactions. In this case, if we're under acidic conditions, we'll form what's called an acetal, where our aldehyde or ketone is going to react with two alcohols. And so we lose the C double bond O, and it's replaced with still having two oxygen bonds, but now both of those oxygens are coming from our alcohols. So we need two equivalents of the alcohol for every one equivalent of the ketone or aldehyde. Now these reactions are catalyzed under acidic conditions. And so what you'll very often see the book doing when it wants us to indicate that we're under acidic conditions, it'll use an H plus in brackets to indicate that we have an acid catalyst. And a very common acid that's used to catalyze these reactions is sulfuric acid. All right, so the mechanism for the formation of these acetals is a little bit long. This is maybe one of the longer mechanisms that we've learned. So I think it helps to break it up into two steps. So first we're going to look at the formation of a hemiacetal, and then how we convert from the hemiacetal to the acetal. So here's the first three steps. And so this is for the formation of the hemiacetal. And this is exactly the same as the mechanism that we had for acid catalyzed hydration. We start with a proton transfer. We then have nucleophilic addition. We end up with this charged species, and so we need another proton transfer to give us our neutral intermediate in this case. I guess I don't want to call it a product because it's not our stopping point. Right, but alcohols aren't particularly strong nucleophiles, so we do this under acidic conditions, where we can, after the proton transfer, we convert the ketone, which wasn't a great electrophile, into something that has a positive charge, is now quite a good electrophile. It's followed up by nucleophilic attack by the alcohol. The pi bond moves up to be a lone pair on the oxygen. And then, because we ended up with this charged species, just like we ended up with when we added water with the hydrates, so then we have a proton transfer to pick that hydrogen off and give us the neutral intermediate in this case. All right, and then the last four steps is in many ways a continuation of the process that we saw in the first three with a notable addition, or in this case, a notable subtraction. So after we form the hemiacetal, we have another proton transfer step where we end up protonating this OH group. Right? OH is not a good leaving group. H2O is quite a good leaving group. And so after we protonate this guy, we followed up with a loss of a water. And so the water pops off, and one of the lone pair electrons on what was the alcohol becomes a pi bond. Now these last two steps are just like the last two steps in the formation of the hemiacetal. We have a nucleophilic attack from another alcohol molecule. That leaves us with a protonated species, and so we have a base come in to pull off that extra hydrogen. As we mentioned in the first video on these nucleophilic addition reactions, a lot of these reactions are equilibrium processes, meaning it could be that the reactants are favored, it could be that the products are favored, and it kind of depends on the conditions. For simple aldehydes, like formaldehyde, these are generally product favored. Although you notice we don't write just a one-sided arrow because we will generally have a mixture of the ketone and the acetal when we reach equilibrium. For most ketones, in fact, the acetal is not favored at equilibrium. And so you may say then, what's the use of these reactions? Well, if you remember back from 1212, we learned ways that we could control the equilibrium. And when we considered this qualitatively, we talked about Le Chatelier's principle. And one of the things that we could do in Le Chatelier's principle, if we could add or remove reactants or products, that could shift the equilibrium to one direction or the other. And so if we can somehow remove water from the system, then that will continue to push the equilibrium to the right and get us to form products, allowing us to essentially force the reaction to completion. So people have developed clever distillation techniques where they can remove the water and then continue to force the reaction to produce products. An interesting twist on this reaction, if we use a diol, so a compound that has two alcohols, we can actually add both OH groups from the same compound to form our acetal. And so when that happens, both equivalents of oxygens come from the same molecule, and so we end up forming a cyclic acetal. The steps of the mechanism are just the same as the ones that we had before. We have 3 steps to form a hemiacetal, and we have essentially the same 4 steps to form the acetal from the hemiacetal. All right, so it's really important to get comfortable in drawing the mechanisms for the formation of acetals, and so I wanted to go through one together. And so remember, we're going to break this up into 2 steps. First, we're going to convert our ketone, in this case, to a hemiacetal. That'll take 3 steps. And then we'll convert that hemiacetal to the acetal, which will take 4 steps. And the first 3 steps are exactly the same as acid-catalyzed hydration that we've already learned. And so because this is a weak nucleophile, the first thing we need to do is a proton transfer step to turn that, this is a weak electrophile. So the first thing we need to do is a proton transfer step to turn it into a strong electrophile. So we're in acidic conditions. So I have an H3O plus that will act as my proton donor. I'll then follow this up with nucleophilic attack of the alcohol. In this case, my alcohol is methanol. And then because I have this charged species that I created, in order to get to the hemiacetal, which is neutral, I need to follow this up with a proton transfer step. So the base that I'm going to have available to me in this case, I can't use OH, I can't use a strong base under acidic conditions, and so my most likely base in this case is the alcohol, and so I'll use methanol as my proton acceptor. And I've formed my hemiacetal. All right, now we have 4 steps to get from the hemiacetal to the acetal. And I kind of break these up in my head into 2 steps. The first thing we need to do is to get rid of this OH. Now, OH is a bad leaving group. So the first thing that's going to happen is we're going to protonate this OH, then it's going to pop off as a leaving group, and then the next 2 steps are the same as the last 2 steps that we had up here. We're going to have the attack of our nucleophile, in this case the alcohol, and we'll have a proton transfer to get rid of that proton to leave us with the neutral product. All right, so first thing, we need to protonate that OH to turn it into a good leaving group. So we're under acidic conditions. So H3O plus can be my proton donor. So now we're going to have a loss of a leaving group. That water is going to pop off. And then one of the lone pairs from what was the alcohol will become a pi bond. And then my last two steps, I'll have the nucleophilic attack from another alcohol, and then I'll deprotonate that. So then to get to my final product, we finish it off with a proton transfer.